Every day, we rely upon products such as foodstuffs, personal products, plastics, and sometimes upon pharmaceuticals. These are all typically made from several materials and manufactured using an appropriate industrial process. Where these are liquids, perhaps with solids, we typically need to combine them, chemically and/or physically, into an intermediate or final product. Mixing them in a container is one obvious method of combining materials and is used widely in many business sectors. Here, we've taken 4 examples to represent the massive array of products and the materials used to make them. Many consumer goods, such as soaps, washing powder, toothpaste and paints, rely upon combinations of separate materials to make these complex products in liquid form, or as a solid, such as powder. Complex chemicals such as plastics are made in the further manufacture of an enormous range of products from cars to TV sets to building materials. Much of our food is made from natural or man-made ingredients using processes to ensure the specified composition. For example, foods such as yogurt, fruit juices, drinks, and baby foods have a precise formulation that ensures the expected taste, composition, and nutritional characteristics. Pharmaceuticals is a global industry in which critical manufacturing processes must precisely synthesize complex medicines. Of course, we want all our processes to work properly, to create the products we're interested in a way that delivers the quality we require, but also delivers environmental goals. An expert cook using a kitchen mixer would just take a look and gauge when ingredients are mixed. This could work in industrial mixers too, but first we must decide what we must look for to ensure that mixing is complete. It's obvious that we can't see inside this industrial mixer. Let's take a closer look at this example. An actual industrial mixer is basically similar to a kitchen version, a vessel with an impeller, but much larger. Since it has to operate at elevated pressures and temperatures, it's typically made of steel or a ceramic. Here we see the top of a typical mixing vessel. Looking closely, we can see some obvious features. Firstly, we see an electric motor which drives the internal impeller shaft. Interestingly, there is also a small circular viewing window designed to withstand the internal pressure. But even if the contents are clear, it will be difficult to see the internal distribution from this one viewpoint. So in general terms, it's not possible to see inside. Materials we need to process vary enormously. Mixing 2 physically similar liquids is obviously very different from mixing a liquid with a solid in powder form. A mixer may incorporate design features to suit specific material types. In this batch process, we ideally expect initially separate materials to combine as quickly as possible, chemically and/or physically, to form the resulting mixed product. We can design specific features to suit different material combinations. For example, when denser material sinks to the bottom, the impeller may simply rotate this around. Fitting wall baffles can eliminate this behaviour. A variety of impellers are also available to suit many types of materials. Some produce upthrust to force denser material upwards to mix with lighter components. Even when the most appropriate equipment is used, we cannot be certain what is happening in the process. For example, temperature and pressure may vary and raw material characteristics may change. Ideally, we would like to monitor the exact details at all points throughout the mixing process, from the initial state until mixing is complete.
Here we see a simple pilot plant vessel, about 1.5 metres in diameter. For operational simplicity, and so that we can observe from above, it has an open top and hence operates at ambient atmospheric pressure. As we look inside, we see the obvious impeller on its shaft at the bottom. We also see that the internal wall has many small electrodes connected to external equipment via cables. These allow us to use this experimental vessel to see inside the process using electrical tomography. Looking more closely, we can count 8 parallel rings of these sensing electrodes. Let's explore a simple mixing process in action. First, we need a vessel to perform the mixing. It will also have a pressure cover. This provides a mount for a mixing impeller driven by an electric motor. We can run the impeller to see it working. We can assemble the parts to complete our mixing vessel. As we close the cover, the internal features and contents of the mixer become invisible. We can now connect pipes to tanks to supply the 2 materials to be mixed. We can use valves to control the flow. Here the valves are closed. The right tank provides material A, and the left tank provides material B. First we'll add material A to the vessel. We open valve A to begin filling. We measure how much we need and then close the valve. We're now ready to add material B and begin the mixing. We've also provided a timer to measure how long the mixing process has been running. Here we'll speed up time by about 1000 to see action that would take more than an hour appear quickly over a few seconds. We'll start the impeller motor and then open valve B and begin adding material B. We've now added the amount of B we need. We'll close the valve but keep on mixing. Now we'll focus just on the mixing and the vessel. So for clarity, we can remove the details of the tanks and valves. We'll just keep on mixing but view the vessel more closely. It must have finished by now, but we have no means of knowing. In general, we could always add extra time to make sure. We can turn off the impeller and hope that the mixing is completed. If it isn't fully mixed, we may have to return the unfinished result to the vessel and continue to mix further. Of course, we could have used our tomographic sensing equipment to see inside the process. Let's use a one-plane internal tomographic sensor near the bottom of the vessel so we can try to see what's happening inside. Here we begin again with the mixer filled with material A, and then inject material B and start the mixing sequence again. Here we see false colours assigned to measured pixel values. The colour indicates the concentration of a specific material. Here, we can assume, for example, that the first raw material A has a blue colour. The injected material B is indicated as a red colour, and the resulting mixed product material as a green colour. Of course, the false colours are used to visually discriminate measured values. It doesn't mean that the materials have these colours. So, we have now gained a major insight into what's happening at the bottom of the vessel. But can we get more data? Let's try the two-plane configuration to see more data, by adding a further plane at the top of the vessel. Once again, we begin with the mixer filled with material A, inject material B, and start the mixing sequence again. We've now gained more insight into what's happening at the top and bottom of the vessel. Is it possible to add more planes to get even more data? We can add 2 further planes to fill the gap and run the mixing process once more. We've now gained a major insight into what's happening within the whole vessel. It may be possible to interpolate data between the planes to provide a complete view. But would this be improved if we had more data planes? At relatively minor cost, we can add as many planes as we need to provide data that we can confidently use to extract 3D estimates. Here we can install 8 planes and then repeat the test. We've now gained significant axial insight and detailed cross-sectional data. What could we do to gain even more insight? We could use our tomographic cross-sectional data to interpolate and estimate a 3D distribution of the process. Here we run the mixing process for a final time, with this feature enabled. We've now seen how IPT data can deliver major insight into the mixing process. We could use the data to assess how well the process is mixing the materials. We could adjust the impeller speed to provide the most effective mixing dynamics for the materials. An obvious point in our demonstrations above is that the allowed mixing time of 100 minutes is significantly longer than needed, perhaps by 30 to 40%. With this advanced information, we could cease the operation mixing when we see that the mixture is complete. This would save plant time, wear and tear and energy costs and lower resulting emissions. It would increase plant utilisation and productivity. It is also likely to enhance product quality and reduce wastage. Of course, it would also be fairly simple to automate the interpretation of the 3D image sequence to indicate the complete point. Let's re-examine how we obtain detailed information on the state and performance of the mixer. Remember our simplest one-plane 2D data? Here's the first one-plane cross-section we measured at our process start time. We'll show it vertically so we can stack time sections in left to right time order. We'll now start our process timer, run our process once more, and extract 10 cross-sectional slices. Here we see the 10 slices dealt like playing cards on a stack. We must remember that this stack gets longer with time and not in space. We can now examine one pixel point in the process to illustrate how we can derive information on the detailed mixing performance. For this specific pixel, we view the product concentration colour value from on each time card. These values form a mixing characteristic for that one point in the process and display this as a graph. Now we have the information on how well the mixing progressed at that selected point. We can do this for any and every point for which we have data. Using our 3D with time data, we can estimate the product concentration for each 3D volume pixel, or voxel, as the mixing progresses. For example, we can now track a selected process target. For example, when 90% of a chosen subset of voxels reach a concentration of at least 90%, we could cease mixing. From our early examination, when we could only guess what is going on inside our process, we have now gained detailed and comprehensive process information.
We begin by looking at several major industry sectors. Industry, in general, is continually pressurised to enhance its performance. Business drivers press for improved productivity along with product quality, with increased return on investment such as process plant. Environmental drivers press for reduced pollution and waste. Energy drivers press for reduced energy consumption and emissions. We can classify and examine these various pressures and drivers in more detail. Here, the red circle represents business pressures which seek higher bottom-line benefits. Our multi-dimensional sensing technology provides key insight to reduce mixer processing times and enhance performance, leading to higher utilization and product quality. The green circle represents fiscal and societal pressures to reduce impact on the environment. Our technology provides information leading to reduced waste and impact. Finally, the blue circle represents pressures to reduce energy consumption and global warming emissions. Our technology provides information to increase efficiency and reduce mixing process times, reducing energy use. We've been working with images. As any schoolchild knows, mixing red, green and blue light gives white light. This analogy illustrates the resulting red, green and blue mixing process improvements through enhanced performance from process sensing technology, represented here by the white outcome circle. In summary, our super sensing information delivers enhanced process mixing.